Now we've talked about polynomial addition and subtraction and multiplication. So it's only right that we talk about polynomial division. Okay. Now, in analogy to division with integers, when you divide one integer by another, you have the number that's being divided and the divisor. Suppose the divisor is b. When you divide them, you'll get a remainder, and the remainder is always smaller than b. It turns out something similar is true for polynomials. Not quite the same, but very similar. Here's an example of a long division, and I assume that you've seen this in high school. If not, you can review here and look at some other examples on the web. So here we have the polynomial being divided, here we have the divisor, and here we have the remainder. And we notice that the degree of the remainder is less than the degree of the divisor. Okay. Now, this process is not unique to polynomials with real or integer coefficients. We can do exactly the same process if our coefficients are in another group, such as Z5. All right, so follow this example through. You'll see we do some strange arithmetic here. For instance, you have 3 minus 4 equals 4. That's not a mistake. That's simply subtraction mod 5. But similarly, we get a remainder whose degree is less than the divisor. Here are some more examples to practice on. And now we have a proposition, very important proposition. Take any two non-zero polynomials, and we're not presuming anything about the group of the coefficients, except that they form a polynomial ring, where the degree of g of x is greater than 0. Okay. Then there exists a unique polynomial q and r such that f of x equals g of x, q of x, plus r of x, and the degree of r is less than the degree of g. Now remember, when we were dividing integers, we had that if we had a equals b, q plus r, we had r was less than b. In this case, we have the degree of r is less than the degree of the divisor. All right, so, and this is true for any polynomial ring. All right, so let's prove first. No, so what do we have to prove here? We have it exists and it's unique. We have a remainder whose degree is less than g, and it's unique. So the proof will have two parts. First of all, we'll prove the existence of the remainder and the quotient. Let's define the following set. This set is the set of all possible polynomials that can be expressed as f of x minus g of x times some polynomial. Okay, so this is a big set, and it contains a lot of polynomials. Now, it's not empty because f of x itself is in the set, and f of x has some finite degree. So there must be a polynomial of smallest degree. Okay, why is that? Well, if it's not f itself, then if there's some polynomial smaller than f, the smallest it can be is 1 or 0. So there must be one of smallest degree. Okay, this means there must exist a q. For this particular r, there must exist a q such that r of x equals f of x minus g of x, q of x, because that's the definition of elements of S. If r is in S, it must have this form. Now what we're going to do, what do we want to show? We want to show that r of x is actually equal to, we want to show that r of x has degree less than g. That's what we want to show. R of x is a polynomial of this form of minimum degree. We want to show the degree is actually less than g. And we're going to do this by taking a q from the process of long division itself. Okay. We'll prove by contradiction. So assume the contrary, namely that the degree of g is not bigger than the degree of r. In this case, we can define some notation. N is the degree of g, m is the degree of r. We can write g as a sum of terms up to degree n, and we can write r as a sum of terms up to degree m. And what we're saying is that n is less than or equal to n. Now, what we could actually do in this case is we could divide more copies of g into r. And how would that work? Well, think of this expression here. Suppose I take bm times an inverse times x to the m minus n times g of x. So I'll write it up here. G of x times bm an inverse x to the m minus n. What's that going to be? Well, it's going to have a lot of terms. What's the largest term? The largest term is going to be this term, an x to the m, times, x to the n. Made a mistake there, sorry. And this also is an n. Missed that. It's going to be some polynomial. Largest term is an x to the n times bm an inverse times x to the m minus n. Now, if you multiply this all together, you're going to get some terms. The last term is going to be what? Well, let me rearrange things a little bit. This an, I can move the an and the an inverse together. I'm going to have bm an inverse an x to the n x to the m minus n. Just moving things around, we have a commutative multiplicative group. So we can do this. Now, here we have bm. These two terms just give me the identity, so I can take them out. X to the n, x to the m minus n gives me x to the m. All right, so what did I have here? When I multiply g of x times this, my largest term looks like this. Now, if I subtract this result from my r of x, what happens? I cancel out my highest term here, and the result has degree less than r. So I get this expression here. If I define r prime of x in this way, this r prime has degree less than r. That's assuming, remember, we're assuming that degree of g is less than or equal to degree of r. As long as the degree of g is less than or equal to degree of r, I can find this r prime. Okay? But let's plug in r equals f of x minus g of x q of x. Okay? So r of x, I'm plugging that into this formula here. If I plug that in, I'm going to find that r prime of x is f of x minus g of x times some polynomial. What does that mean? That means that r prime is also in S. You look back at the definition and see. That's how S was defined. If I can express a polynomial as f of x minus g of x times some polynomial, it's in S. And r prime fits the bill. F of x minus g of x times some polynomial. But as I mentioned, once you do this, you're reducing the degree. The degree of r prime is less than the degree of r. This is a contradiction. We chose r of x to be this element of smallest degree in S. What does that mean? Go back and see where we made a mistake. The mistake is when we assumed the contrary. This assumption cannot be true. The degree of g must be bigger than the degree of r. Okay? So that gives us, by contradiction, our proof of the existence of a remainder polynomial whose degree is less than the degree of g. Not done yet. We want to show that this r is unique. Just like when you divide integers, the remainder is unique. All right, so let's see how that works. In order to show that it's unique, well, suppose that there's two different ways of expressing f. And both of these are remainders, and both of these are quotients. Okay. Now remember, we're presuming that the degree of r and the degree of r prime, must be less than the degree of g. Okay? Because they're both these remainder polynomials. So suppose I can express f in two different ways with these small remainders. And suppose the remainders are different. Well, if you rearrange and bring the r's to the right and everything else to the left, you get this expression here. Now, you have g of x times some other polynomial equals the difference of remainders. If this other polynomial is not the zero polynomial, what does that mean? Well, then you're multiplying g by a non-zero polynomial that you get something that has degree at least as big as the degree of g. You can't reduce the degree by multiplying a polynomial by another polynomial. All right? So the degree of g is less than or equal to the degree of this product, but we just show that this product is the difference of the remainders. What do we got here? And the degree of g is less than or equal to the degree of the difference of the remainders. But both of these have degrees smaller than the degree of g. How can you combine two polynomials with small degree and get a polynomial with large degree? Can't do it if you're just using addition. This can't possibly happen. So what's the problem? The problem is we assume that there are two different ways of expressing f. Can't be true. It must be true that the two quotients are the same and the two remainders are the same. Here we have a unique remainder and unique quotient when we're dividing polynomials. Okay.